So we applied Newton's second law, and we got some interesting results based on what we obtained. Of course, in this course, we are not actually asking you to solve this kind of differential equation, but you can do it, I mean, if you like. All right? Then, what about this one? What about this one? Depending on the problem, depending on the question you have, sometimes you have to solve this, or sometimes you don't have to solve this. What about the T? What is the tension? When the tension will be the largest, okay, then tension is equal to mg cosine theta plus mr theta dot square. That means tension would be very large when theta dot is hit the maximum. Okay, when the theta dot will hit the maximum. Well, physics says when we move down at the bottom, okay, theta dot is a velocity, right? Velocity is change of displacement. When pendulum move over there, theta dot is maximum, or theta double dot is maximum. Right over here, when the pendulum is stopped, the theta dot is maximum, or theta double dot is maximum, or theta is maximum. Theta is maximum. Okay? So I want you to draw the picture, okay, of a pendulum. And then you can see when you got maximum tension. All right? You can do it. And another interesting observation we can try is, what if I take a moment with respect to 0? Because those are vector quantity, I can take a moment with respect to point 0. This is very important. Try. Take a moment with respect to 0. What you will get? Okay? So I'm taking a moment with respect to 0. That means I am taking r vector with respect to all the forces. Okay, this is moment vector with respect to 0. And you learned about the moment, right? Okay. Up to now, we saw all the vectors according to the sort of two-dimensional coordinate. But because those are vectors, Newton's second law is simply expressed as vector equal vector. Right? Then we can take a moment. So this is a moment. And that has to be equal to the summation of Fi will induce the mass times acceleration, right? So maybe, can I write like that? Indeed. Yeah? So what if I apply that one upon this picture? What I will get? I will get moment in this direction, I assign the sign convention of moment. Okay, that is positive. Then I have mg sine theta multiplied by r. That is the moment due to mg sine theta force in this direction. That has to be equal to r times mass times acceleration, mass times and acceleration in this direction. That is mr theta double dot, but it has a direction over there that has to be minus. If I use this is a plus. Okay? So what do you get? I got same result, right? Theta dot plus g over r theta equals 0. So depending on your interest, you can take a moment to all the vectors, right? By using this approach, you don't have to worry about handling tension. There's just some advantage. I say again, we express the Newton's second law in terms of all the vectors. Okay? Then we can use every tool that is good for vectors. One is I can take a moment. Right? And then we call this angular momentum with respect to time, rate of change of time, where h0 is, in strict sense, h0 is moment of linear momentum. In other words, that is r mv. Why we are handling this? As I mentioned briefly, sometimes looking at the dynamic system in terms of moment it gives us more insight and understanding. Sometimes that is very convenient. Right? Then let's take ddt on both sides. All right? Then this is h0 dot, rate of change of angular momentum. Then I got, take a derivative with respect to position vector, that is velocity, and take a derivative with respect to this one, and this is what? 0? V square or 0? 0, right, because those two vectors are collinear, in parallel, same direction, therefore cross product is 0. Okay? Okay. Cross product certainly exhibits some sort of physics related with rotation. Therefore, that is 0. And this is time rate of change of angular momentum. So in conclusion, we can say again this. Moment with respect to certain point would be same as rate of change of angular momentum with respect to certain point. Oh, again, we have a very simple equation. Okay, very simple equation. Then how to apply that simple equation in real dynamics? Let's go back to the text again. See some simple problem. Okay, let's see this problem. Here is frictionless table. Again, and there is some hole. If I look at the ball, there is a table, there is a hole, and this ball is moving with a direction like that with initial velocity v0. There is a code, taut code, which means that inextensible, and I'm pulling down the cord. And I want to know how this mass is moving at certain position. Okay? So there is a mass, there is a cord, and I'm pulling down the tension T. Right. If I take a moment with respect to this point, okay, that obviously angular momentum change with respect to time. I just repeat to write down this equation. And note that the moment is R cross product every possible force. So I look at every possible force. Okay, there is a force mg, and I am taking the moment with respect to that. Okay. Then what I see is there is a mass mg, and there is a tension, and there should be another force N, normal force, and there should be some friction force, but I neglected. So what I can observe is that no moment in this direction. Right? There's no moment in this direction. So moment is 0. Therefore, H0, is constant. So I can immediately see that the small ball rotating on the surface by conserving angular momentum. What does it mean? To conserve angular momentum, that is R multiply mv, right? Because I'm pulling down the cord, the R is decreasing. To conserve angular momentum, the velocity has to be increased. So what's going to happen on this frictionless ball, or rotating on the table case, when I pull down, the ball is rotating faster and faster speed as I decrease the chord length. That's interesting. Yeah, that's interesting. Many athletics wisely use the conservation of angular momentum when they demonstrate very exciting performance. Okay? When they rotate at the initial speed like that, and then if they reduce the R, because angular momentum has to be conserved, the speed has to be increased, therefore you will see very fast rotation and small rotation. Right? Okay. Also, you can see many other things. For example, in a diving, when divers shrink their body, then the rotation increase. When they elongate the body, rotation decrease, so on, so on. Reason is because there is no moment free. As this equation said, if the moment is 0 with respect to certain point of interest, then h0 dot, which is simply rate of change of angular momentum with respect to time, has to be constant. So we call angular momentum is conserved. Or in short, we can say conservation of angular momentum. Okay? That is interesting outcome by seeing Newton's second law differently.